Well, look-a here. Back in school. Even from your own desk chair at home. Isn't that nice? Well, nice to talk to everybody. Let's pretend to see each other through our little notes here, our little classroom here. Hopefully everybody's staying safe. Social distancing. Social distance is kind of a strange concept, huh? My daughter was yelling at me, Dad, why do you act like everybody has corona? That's what social distancing is. You got to pretend everybody has corona. So don't be getting together to play your sports. Don't be getting together to hang out, have little parties, any of that other nonsense. Cut that out. Um, just a side note, kind of a good time to be a distance runner. You can do that all by your lonesome and stay fit too. Anyway, let's go on over here. All right, these are our notes, and you have the Unit 7 notes at home. In case you don't have them home, they're in the drive. The link to the drive is on the daily physics workout, as it always is. So go to Unit 7, go to Notes, pop it open. If you got to, hopefully have the copy. If you have to print it, you can do that. You can write it on paper. You don't really need to print anything. So might make it a little less convenient, but if you're without a printed copy, you can do this on paper alongside it and always refer back to the actual files in the drive. And by the way, the school might be able to help you out if you're without an actual computer. If you're only working through your phone, it's a little limited. All right, so I'm going to have you jump down to page 23. One page of a little bit of talk and one page of calculating. Nothing special today, but we're going to make a connection. So down on page 23, here we are. What you'll notice is we're going to finalize the connection, so to speak. So you took a quiz, or you're about to take a quiz. Hopefully you're done if you're watching this video, on all the different ways you calculate work, and particularly force-specific work. You also took a quiz on all the different ways you calculate energy. Now it's time to connect them. If you remember, there were different types of energy. That's up here. So we were talking about that back in the early part of the unit. We also talked about how energy moves around in a closed system. We did that law of conservation of energy. And we started to talk about how energy can be changed. And we didn't get too much into that, but basically we said when there's an external force, when a force comes in from the outside, when Dumbo the elephant comes in and whacks into the spring toy, well, that changes the energy of the system. So that's basically as far as we got with our work energy connection, then we cut it off there. We jumped ahead, we spent a lot of time there, just finished our quiz on the different types of work. The free body diagram was really the focus of this section. You get your forces right and you get your works right. And there are different types of work. Do not just generically solve for W. You gotta know which one they're talking about. Common mistake I saw in the homeworks turned in is people writing WN as in work of the normal force when the question was asked about the work done against gravity. Please don't mix those up. They are definitely not the same thing. All right, machines down here, we'll do a little bit on it. It's really nothing special there. There's no new physics there for you to worry about. Just a couple new terms. And then power is pretty easy to talk about. You've already done a 7 something A. What was it? 710A, 70, whatever it was. You've done an intro with power. It's pretty easy within this course. All right, so let's get on to this work energy business. So what's so special here? Well, basically, here it is. You have this equation. This is the one that's in your reference table. Some of you actually have been using it in the homework a bit. W equals FD, you know that part. Energy, you know that part. Now let's put it all together. And this little section over here specifically, this is fantastic, truly. Took a little time to come up with this nice connection here in the table you're about to see below. It's worth your while to think about it, what these spaces are saying right here. So, what's that, a little highlighter? Cool. These little spaces right here are telling you that the types align. So yes, W equals FD, but it's a little more than that. W equals F times the D that it aligns with, the D that it causes. If they're at 90 to each other, 90 degrees, they don't align, and there's no work. And then that will cause a change in energy for that object, that system. Now, the spaces are for the type of work. If the question or the type of force or the type of energy, because they always go together. If the question says, Work done against gravity, you're going to put a little g in here, a little g in here, and a little g in here. We don't write as delta EG. That we actually write as delta PE. Sometimes we've been writing it as delta PEG. So the delta E, sometimes there's a P in front of it, K in front of it, PES, whatever it is, but the idea is the same. Whichever force they're talking about, gravitational goes with gravitational work, goes with gravitational energy. If instead it's not gravitational, maybe it is frictional, maybe it's a frictional force, well then we don't worry about FG, we worry about FF, which will give you the work done against friction, which will give you the change in energy of friction. In that case, we actually call that delta Q. So the energies, the symbols are slightly different than just delta E with a subscript, but honestly, you could write it that way. You could totally write delta E G for gravity, delta E S for spring, delta E Q or F for internal or friction. So these are pretty straightforward here. The terminology, the notation, don't get caught up with that so much. Get caught up with this idea that the force, the work, the energy all align. Now here's the beauty of this multi-equation. Basically, you now have more than one way to skin a cat. So let's go down here. Check this. Now this is really, look at this. It's like the Rosetta Stone, and this thing is beauty. All right, let's look at one piece at a time. You already know, let's go over here. You already know W equals FD, and that's really this whole section. So you see, just running from right to left instead of left to right, W equals FD written out 4 different ways. This is what you used on your quiz. So if it's gravitational work or if it's gravitational force, it's that first equation. WG is FG, and it always lines up with a vertical displacement. If it's spring, which is not asked that often, WS is actually the average force in the spring times X, with some of you notice that there. If it's work to accelerate or work done by the net force, you get a W net, and that's based on the F net. And of course, friction is based on the frictional force. So we have that covered. The other piece that we have covered is right here. That's what we spent the first half of the unit focusing on. Change in PEG was mg delta H, and so on. If you recall, right, here we go. This one and this one, for those of you who might be going into college physics or taking physics in college, if you recall, delta PES and delta KE aren't technically half kx squared or half mb squared. There's a little more of a complicated equation. It was the in parentheses, x final squared minus x initial squared multiplied by that 1/2 k. And the v had the same thing. You don't have to worry about that in this course. And the reason is we always start or end at 0 stretch or 0 velocity in this course. So basically the equation you see there will work. We didn't have anything else for the delta Q. Here's the new piece. And this new piece really is magic. And really, it's worth taking your time, rewatch this if you have to really think about it. Here's the new piece. Right here in the middle. There it is. The new piece is saying, work done against gravity will cause a change in the gravitational potential energy. Work done on a spring will cause a change in the elastic potential energy. Work done to accelerate or net work done on an object will cause a change in its kinetic energy. Work done against friction will cause a change in the internal energy. In fact, those causes are exactly equal. The beauty of this is you now have just introduced multiple ways to skin this here cat. So how do we do that? Let's see. We'll go over here and put a red pen on this, John. Here we go. So if I ask you for delta PEG, in the past, you would have gone to MGH. Now you can also go and say, oh, do I know WG? Because that would give it. And even more so, I could go do FGDY. So basically, you just have more options here. The PEG one's kind of easy. One that's actually great is really the delta KE. What's the change in the kinetic energy? Oh, sure, let's do the half mv squared. But if those aren't your givens, well, maybe you know the network. Or if you don't know the network, maybe you know the F net times D. And the truth is, if you have F and D and they ask for delta KE, you probably would have said, oh man, I need M and I need V. Well, now you don't. Now you need F net and D because all of these are equivalent. And so the real beauty here is taking this equation that's given to you and putting subscripts on it. Now, if you notice, what they did not particularly write in your reference table, and it makes sense they didn't, is they didn't then write that this is equal to whatever it is, the mgh, the half kx squared, the half mv squared, and so on. They don't have that written there because they're all in different forms. But there are really 4 pieces to this multi-equation, and you can bounce between any of them. Here you saw the first one I was asking about the PEG. Well, I could equally ask about the WG. Well, one way to get that, of course, is F times D. But another way is by knowing the delta PEG. Or if your givens call for it, mg delta H. So you can go between any of these. Just pick 2, equate them. This is where the givens are really going to come into play. Now, this down at the bottom says yet. If you remember, there are a bunch of not yets. This says go back to notes, pages 16 to 19, and also page 12, and fill in the changed and not yet bars. All right, let's go try that out. Let's take a little gander. Maybe we can go backwards on this one. Some of these we might do faster than others. So you already have completed notes, page 16 to 19. There's a separate file that's in your notes folder on the drive, unit 7. Let's go check this one out. So, what has changed? That's what this is talking about. So what has changed? Well, if you look at these over here, well, what has changed over here? Which energies have changed? Well, if you remember from these, this one actually no work was done. This over here, sorry. There we go. This one, if you remember, there was no work done in any regard. So what changed? Nothing. None. And it makes sense because if you remember from this picture, the weight was held still. Displacement was 0. So the WG was 0. The work done by the normal was 0. The net work was 0. All right? And that's, we're probably not going to go through all these right now. I'll fill them in and you can just look at them clean in the notes. Make a cleaner version than what you see sketched here. Even this one, look at the planet in the circular orbit, whatever it is, moon around a planet, planet around a star, whatever it is. So what has changed? Well, if you recall in this case, WG, we had the force of gravity was pointing in here. So WG actually was perpendicular to the displacement, so there was none there. And then there was W net. Well, F net was in, but it was still perpendicular to D. W net was actually equal to WG. That was also 0. And what changed? Well, there was no work done, so none of the energy is going to change. And that's one of the beautiful things about orbit, for example, is that based on this, it doesn't need an engine. Things can just go because there's no work required. This page here was more of a trying to trick you. This one down here, we talked about person pulling. They're putting a lot of effort on it. However, it's crazy glued to the ground, so the displacement's 0. So all of the works, are going to be 0. WG, W normal, W of this external force, W from the glue, which is kind of like a friction, W net, they're all going to be 0. And what changes about the energy of this box? None. And when you get to a higher level course, you might talk about the box stretching, but that's not for this course. Even this